toilets, and we have eco-friendly. So to innovate, change something established by new methods and ideas or products. That's what they're doing. This is a trend that's catching on. Integrate. I have to integrate to the existing grid, the power supply and everything else. But I didn't let those limitations change my design, right? I did my design by innovating. Adapt and stagnate. Look at this trailer park. Everybody took a container and they said, we want the same thing. All that they did was they took the smallest minimal change to avoid cost. Nobody wanted to redo their trailer. Nobody wanted to do it. So we adapted it for a purpose, but what that leads to is it leads to stagnation. You cease to develop because you're carrying so much technical debt, you almost feel like you can't get rid of it. So here's an example. Everybody talks about this. I'll go through it lightly. Blockbuster is one of the biggest failures out there of adapt and stagnate. What they did was their business model was brick and mortar, and they charged a ton of money for late fees. But what happened is consumer behavior changed. Their expectations of how I got videos, what I wanted to consume it. Go back to my definition of digital transformation. Netflix innovated. The distribution channels, they weren't able to interact with customers in the channels that they desired, and they weren't able to get into the market quickly. So what did they do? They started a mail-to-home service, right? So now they're taking a brick and mortar and they're trying to now go, yeah, we can send you discs. They tried to eliminate late fees. That cut $200 million a year from their bottom line, which even created more problems. They entered into the movie kiosk. Now they tried to compete with Redbox also. And they started a streaming service. And we all knew what happened to Blockbuster. They basically went out of business. It's a sad case, but it's something that you have to consider yourselves when you're making changes or decisions for your own business. A nice statistic from PwC up here, and this is what I believe in too. An innovation strategy is not a business strategy. The other thing I want to tell you is your cloud migration strategy is not a modernization strategy, because your cloud migration, think of the word migration. I'm taking something that runs on my data center, and then I have to accommodate it to live in a perfect environment. AWS, Azure, Google Cloud. So what we want to do is, that is adaptation. If you're going to have a cloud strategy, define your cloud strategy and allow it to be perfect, and then make integrations to bring your other legacy workloads along. So how are companies facing the challenges today? Well, the changing customer demographic and expectations is probably the most prevalent, right? We have to adjust to how consumers want to do it. I'm going to give you an example in a short while in the insurance industry. Nobody wants to go to an insurance agent anymore, right? You have e-insurance, you have a number of these others, you answer 4 questions, you can get life insurance. Complex decisions, we talked about that a little earlier. How do we reduce the strategy and the decisions so that everybody in the IT, everybody in the business, and everybody in marketing believes this rule is that rule? Time to market. If things are spread out all over the place, how can you quickly adapt? You heard Berserta talk this morning about your velocity, right? Your sprints, developing stuff quicker. Well, time to market and capturing new markets is also dependent upon your business. Are we in an IT organization ready to deal with and ready to capture new markets, or do we have internal fighting? Manual time. There's sometimes, I call it shadow IT. This mainframe system does this SaaS-based system does this, and now somewhere in between, it stinks. So people take data from one, they create spreadsheets, they create access databases, they manipulate it, and then they shove it into the other system. That is technical debt. That's not that manual time, if it's not taken care of, can erode it. Consistency, risk mitigation, balance and knowledge, right? Experience and knowledge. Do you have the people? That's another thing I'll talk about today is your staff and your employees are your largest asset. You need an organizational development plan. All of these new technologies have introduced new skill sets. So a system operator, a Linux administrator, a programmer, somebody that's responsible for your source code control and promotion, they should have different jobs. And we should remove and add different responsibilities. But if we don't define the positions, like if I said, let's go out and implement OpenShift, if I don't tell you that these are the 5 positions that you need, and under those 5 positions, these are the skill sets that they need, when I leave, you're gonna be unhappy because you're gonna take your individuals who have done virtualization, manual patching, and a number of things and try and apply those same skills to a new process. It doesn't work well. We've had great implementations, but we've had angry customers. And the angry customers are because they didn't invest in themselves. They didn't invest in learning and transforming their organizations. Here's another slide from my insurance presentation. I thought it was relevant because most organizations have the top things. What's your priorities? Improving the experience of our customers, right? I do work and I buy things with people that make it easier for me to conduct business with. And because of that, my revenue is gonna grow. If I take all the approaches that we're talking about today, we're gonna improve our ability to innovate, and we're gonna improve our products and services. So these, while they're addressed to the insurance segment, I believe that they're also relevant for every business that's in this audience today and watching online. And here's another great statistic, and I'm not sure if it evenly conveys over to everybody here, but almost 2/3 of your expenses of your IT budget goes to run your existing business. And that's because we're either unwilling or incapable of changing how we address the markets and how we spend our money. And at some point, we have to shift that number. We have to shift more into innovation and take less out of operations. So what I want to do is I want to define a journey of knowledge. I believe that knowledge management is the foundation of artificial intelligence. And let me explain to you what I believe knowledge management is. I'm going to start with Apache Kafka. This is a new technology. 35% of the Fortune 500 are using it. Some are using it heavily in production. Some have mastered it. Most have not. Most are in an experimental phase. LinkedIn created it in 2011. So they have things called streaming data pipelines. This is where data becomes the event, right? As information flows in, we're going to have listeners, and we're going to say, well, that's an insurance thing, and that's a policy change. I have to do something about that. Versus it's going to get into a program, and then you're going to embed logic, and you're going to do conditional breaking. It allows applications to, here's the important part, react to. When that data comes in, these events and microservices react. They wake up and they perform some service, either transformation, enrichment, or some processing. And they transform data, and data is information. So basically, it's almost like a message queue. Publish and subscribe, but instead of fixed data, it's streams of data. Persist streams in fault-tolerant and durable way. This information can be spread across one data center or multiple data centers and multiple clusters. But because of how they keep track of it, they will never go out of order. And when they're down, they're durable. When they come back up, they will replay and they will execute in the same fashion. So these records are processed in the order that they receive. The components of Kafka that you should worry about, it's a clustered, distributed system. But what I like is I consider it a continuity of operations plan. If I have message queues, I have to make them durable, right? I have to store the data someplace. I got to make sure that when it comes up that they fire the messages in the order that they're received. If I could take that pain away, then I actually have a business continuity of operations. I've adopted a strategy where, based on events, I know that when my business comes up, my business is going to process again after that adverse effect. And there's a key thing. There's a key, there's a value, and there's a timestamp. And that's what allows me to keep my data in sync. The other important aspect, it's basically got 4 APIs. It's a producer. It publishes information to one or more topics. I have data, and I just want to shove it out there. It has consumers, right? I like People magazine, so I'm going to consume whatever People pushes out. I like to see it when it comes. And then what I could do is I could even repurpose it onto my blog. Suppose I'm somebody that goes, I read People magazine, and I write a blog on celebrities. So I'm going to consume the data, I'm going to enrich it, and then I'm going to republish it. And then the stream, which is actually the contract between the two microservices. And then the connector. The connector is important because we talked about technical debt and other legacy systems. It's going to enable you to build reusable producers and consumers. Producers of information and consumers, but they won't be off of normal data streams. They could be a relational database, they could be log files, they could be any persistent storage mechanism. Okay, let's talk about the communication gap. This is prevalent. It's been going on since IBM created computers and a long time ago. We don't have the same vocabulary between IT and business. What I consider a customer, somebody doesn't consider a customer. What it also does is it gives me a different understanding and perspective of the problem. Somebody in IT wants to program something. Somebody in business wants an outcome that could serve their customer. The other thing is lack of visibility across the entire enterprise. That's without the process management, right? One group in business thinks it's done this way. Another group in finance thinks it's done that way. It's confusing. How do I get them all on the same page? And because we failed, and we all know as IT, we always fail. The statistics are out there. What is it? 3/4 of the IT projects fail and never come to fruition. Well, what you need to do is you need to build new bridges and new gaps. You have to take people out of IT and people out of business and create another functional group that is going to start talking about the next subject. And it's called knowledge management. So hopefully everybody understands the scarecrow from the Wizard of Oz. But knowledge management is the basic process. We have to capture, distribute, and use knowledge. It's a discipline. It's not a program. It's a discipline of how you as a company will take that information and implement it. Well, where are we going to do it? We're going to identify it, we're going to capture it, we're going to retrieve it, and we're going to make it part of our informational assets. We're going to make it important to our business and then provide some taxonomy to it and get it. And what we want to do is we want to capture, here's the one, uncaptured expertise and experience in individual workers. This is your shadow IT. That's what we have to get out. So when the guy goes, if I only had a brain, if I only had a central knowledge, because right now, give me a show of hands, how much knowledge is wrapped up into if-then-else's and application programs? How many guys? Yeah, a lot of them. How many people use Oracle stored procedures or packages to write business logic? Bunch of you, right? So think about that craziness. I have to go from an edge computing, right, from a mobile device all the way into a persistent data store. I got to go into a database for it to tell me where to go next. That's just broken logic. That's just broken design. So we have to have, remember, new models and new techniques. You have to get all of your knowledge into your brain. I don't store my credit card information in my fingertips. Well, with Apple Pay, maybe I do. You know, you can't store everything in different disparate compartments. If my brain is my knowledge management system and my mouth is my API, if you ask me a question, my knowledge management will provide you the same answer. And if I change what my knowledge is, my mouth will say something different. So if you have to look at it in that context, you're trying to build your organizational's brain, right? You're trying to create, and my wife will argue with you, I don't deal well with stress with my children, so I typically fly off the handle and then come back to normal. But that's the process that I have. And sometimes it's immutable. I do it all the time. So this is something that we say. We want to have a single source of truth. By creating a knowledge management program, knowledge is developed by knowledge engineers. A knowledge engineer is a BA on steroids, and it's a developer that comes down to the middle. They both share the same principles, the same guidelines of what they want to do. It is exposed through APIs and consumed by developers, going back to the Bezos. So if we have a group that focuses on creating microservices that react and that transmit, that process and affect data, if we expose those in a business context of an application programming interface or a set of interfaces, and then we allow our developers to consume them, think about the efficiencies that we've just created for software change control and what Burr was talking about today. How quickly can you push? Some people were, what, 18 months? This is the unicorn, in fact. If I could get this, it allows you to accommodate change without impeding by technology limits, because the technology is the knowledge management. And collaboration allows us to standardize our processes into a single source of truth. And the one that I like is transparency. When you see this, nobody can say it's different, right? Because it's not buried in a persistent data store or a programming interface, or worse yet, some offline service that we use. This is what I believe the knowledge-based lifecycle is. You have a concept of operations. What does it do? It gives us a shared business vocabulary. It gives me an organizational concept of operations. Everybody should have the same thing. It gives us well-defined process flows in our workforce, and it allows us to build KPIs within this. So why is there the middle model? The concept model can be as large as you want. That's conceptually how our company operates. The domain model over here, the domain is multiple. Like your microservices, make them as small as possible and make them single-focused. You'll have multiple. Decompose your big problems into manageable models. Because if you don't, what's going to happen is you're going to go back to the same mainframe and waterfall effect. For me to change something, I'm going to have all of these other interconnected devices and programs that I have to validate and change. Where if you look at my interest calculation example, if I just change that one component, I could do black box testing. I could test it on the front, I could test it on the back. And every consumer of that API, once I validate that it's done, will be able to have the same answer, and we can have confidence in the software that was developed and put out there. And then the last one is your rules implementations. These rules may be implemented in one or more business-centric services, but it's still the same rule, right? What we can do, it's a call out. But the 360-degree feedback will go from here to the concept model. You've seen GDPR, right? Everybody throws up the privacy. That was a change in privacy that affected all businesses. Imagine if you're in some regulatory or some business context that says we've just made a change in the subprime lending or how we have to qualify people for mortgages. Imagine if I had to go back, and that will change. It's not a domain. It's not a difference in my business. It's a change to how I have to operate my business. So changes in rules that are outside your company may affect how you conceive your operations or create new business models. So the next thing I'd like you to look at is you have to go into a knowledge-based lifestyle, a knowledge-based system, and we call it knowledge-based IT. You should be doing these. You should have design processes. I've heard people today talk about models and methods, right? Use existing models that are out there. Use design patterns. Don't try and create them yourself. Software tools, decision support mechanisms, and systems architectures. Each one of these, just your knowledge, this is DevOps. We're fine with DevOps for automation. We're fine for DevOps for pushing. With that new team, why don't you do DevOps for knowledge? Why don't you have a team that says, you know what, we're going to keep iterating on what we think our business does, and we're going to keep refining it until it's perfect. And at that point, it's no different than getting your analysis, making designs, making implementations, testing, and evolving them until you're a smart running system. The disciplines of knowledge management are like you got a cornerstone, right? Compliance, implementation, policies. But what it does is it's understandable, it's maintainable, and more than likely, it's extensible. And it relies on systems and software to integrate, here we go back to the other model, domains of knowledge, allowing for dynamic changes in both process and decisions. So in Red Hat, we have Process Automation Manager. And underneath Process Automation Manager, we have Red Hat Decision Manager. So it used to be called BPMS, and then people are familiar with the upstream, which is called rules. So BPM allows us to have a framework for repeatable and a common pattern. Gives us predictability, right? We can see it, we could follow it, and we could watch the flow of end-to-end working data and clearly define paths of how that we create this. Well, what we have to do, though, here's something new that came out in the latest release of Process Automation Manager. It's called the case management and a case file. It allows me to take either connected, disconnected processes and compose them. Some may not have sequential start and end points, but what they do is it allows me to take a real-world application, let's say an insurance case, and I'll show it to you in a minute, that processes can run for days, right? It's not a sequential request-reply. It is a request, and then I'm waiting for some other outside source to fill it in. It manages one-off situations where the process can't be predicted in advance, right? It's not a stream, it's not a flow, it's not an if-then-else decision. It's a tertiary. And here's the most important part. It allows me to compose loosely coupled process fragments. If I have an application process and I'm an insurance carrier, what do I care if the application process grabs it for life insurance, home, auto, or what? I'm still collecting it. So if I define that one process, I could have different cases as they apply for it, and I can embed that same collection process for that automation. And guess what? We're not writing it 5 times. The process is still managed. I still have my KPIs. I know where they're at, and we could basically track it as a business goal. In life insurance, and this is what I've done, these are diagrams from Decision Manager and where they have the asset repository. You have risk mitigation with doing decision management or rules, because in the insurance industry, we developed at Visuri, this is one of our components, we took rules and we developed a dynamic questionnaire. Instead of writing your applications and you having them all done in JavaScript, Angular, or React or something, what we did was we said, BRMS holds all the questions. They know what question to ask, they know what answers are possible, and then based on the answers, we know whether or not a recursive question will come up. So what we're trying to do is we're trying to stop developers from coding applications. And this is dynamically rendered. Once somebody answers a question, I send the answer back to the rule engine and they said A. And then based on A, I may send them another question. Or if that question was sufficiently answered, I'll just move on to my next set of questions. What it does for you, and I'm sure that you've all filled it out, you can't capture all of these questions. They'll go, fill out your name, and are you a military veteran? And if you check yes, answer the next 5 questions. So you have to read and interpret. Remember that we're going for consumer experience. Imagine if the system just threw these things out there and did it for you. So what do we want to do is we want to improve user interface and experience, especially with changing demographics, Gen X, Gen Y, and especially in millennials. Millennials, not in a negative sense. We just have a new consumer base that has been raised in and technologies, and they're expected. So if we're brick and mortar organizations, we need to change. Otherwise, we need to innovate and integrate. Otherwise, we're going to adapt and stagnate. So let's talk about machine learning and artificial intelligence and building on Kafka. So in my business transformation, we did this for a Fortune 100 insurance company. They're a large mutual undercarrier. And what they have is they had a limited supply of knowledgeable underwriters. It's taken them 6 weeks or longer to train somebody. And what they did is, because nobody knew it, they had inconsistency of risk ratings. And then they have something called adverse selection. Because they were so junior, if they did not ask the right question, they could have pushed it all the way through. And this person could have been a smoker, could have had a previous condition, and they let somebody in that shouldn't have been let in, which led to losses. And it's all about training, process, and knowledge. Suppose that the system enforced process and knowledge and decisions. It would reduce to have me having more knowledgeable infrastructure. The system is in that effect. So what we did was we applied actuarial guidelines uniformly to evaluate risk. We used it to validate both data and eligibility. We codified their internal knowledge into a central decision system. And then we orchestrated the processes across all stakeholders, from agents to underwriters to actuaries. And this is what it looks like. If you fill out your name, what will happen is the validation over here will immediately say you have to enter. So this is coming from the rules engine. The validation is making sure that the question that was answered is correct. And what I said before is, if I answered, have you ever used tobacco in any form? If I said no, these questions would not exist. They just skip. It'd go to the next question. If I said yes, then it's going to condition, it's going to ask me these other questions. Talk about user experience, talking about improving process flow, and the validity of the information. Microservices, we heard a lot about them today, right? We want to go from the monolithic, where the mainframes, the old Java applications and such, UI, business logic, and data layer are all in the same, and we define that as a process. Because of this, this allows us to have auto-scaling quickly with inside of OpenShift, right? We have the ability of giving our containers scale out and scale up. We have the ability to leverage and integrate InsurTech offerings. We are able to support third-party data providers such as MIB as mortality, division of motor vehicles, and motor vehicle reports, so that if you have accidents and such. This is an actual diagram from Redhat Process Automation Manager. So what we've done is you can graphically see, now over here, these are sequential. These are actually ones. There's no start or end point. There are different milestones, milestone, 5, but we have decisions. Anything with black is a sub-process underneath that's composable. So calculate insured risk, calculate RAB, MVR, determine if underwriters should review. These are all others. Also, you have an escalation path if nobody understands. So the concept of a case, you can take it in any context of your business. You will define what an actual follow-through or a case is. You got a case file of everything. You can have structured and unstructured data. The other thing that Kafka and these artificial intelligence projects allow you to do is because the data streams are stored in durable streams, they're offline. We can replay them. If we took this, we actually did this, and I'll tell you, we did it by accident. This large mutual insurance carrier said that we wanted you to prove that all of our rules work. So what we did was we took all the policies that we were going to submit and eventually evaluate, and we offlined them. And because we did that, we were able to run them through the underwriting guidelines multiple times. What that allowed them to do is to tune the rules to produce the best outcomes. If the rules were embedded in an application or spread over multiple systems and databases, I wouldn't be able to do that. So underneath our life insurance policy, we were able to say, suppose I don't think vaping is that bad, right? At that point, I may have disqualified all these other people and lost millions of dollars of life insurance policies. But if I change those rules and then I resubmit them, I could do a trade-off as an underwriter to say, if we lessen the guidelines on vaping, we can have $8 million more of policies at this risk, or we want to run them. It gives me the ability to look into my business. Now, Kafka, right, can replay or process historical stored data to improve the ability for trade-off analysis. I mean, think about your business. If you can go, hey, what if? But it has to be designed. If you don't take these from an infrastructure perspective, knowledge, rules, decisions, and processes, you can't get to use Kafka. You'll just increase your technical debt. So coming back to Nirvana, and I want to make sure that we're representing this right. These things on this side, the green boxes, everything is a microservice. These are microservices. So what we've done is we've taken the green. We accept data from RESTful interfaces, right? You heard about them today. These RESTful interfaces collect the information and they send them to our Kafka streams here. These Kafka streams write them to an application processor which feeds a Red Hat Process Automation Manager. These are also microservices. Business rules is microservices. And then what we have is we have a feedback loop. These actually then publish the results back to the stream, and we find out which applications were approved and which applications were rejected. And then based on that, now let's talk about machine learning. From that, I can take approved applications. We don't write any code. It comes down, it says, write it to a new Kafka stream. Because we approved them for life insurance, if my motor vehicle reports, if all of these were capable, what's gonna happen is I'm gonna cross-sell this person. And these are different algorithms. It's beyond our talk today, but machine learning is algorithmic. I like symbolic because it's easy to do. It's a natural first step as you go through. And then after the cross-sell, we can then email people offers and incentive to purchase. So we're getting ready to wrap up here, but let me tell you about two of our customers. You know, you could say, great, Joe, you've talked about this. Let's talk about where we've done this and where others have done it. We're all used to airline travel. We used to stand in line. We used to think paper tickets were great. Interacting with consumers and the device of their choice and how they decide. When I travel here by plane, I don't talk to an agent. I don't talk to an industry person. I don't talk to I have Clear also. I don't talk to a TSA agent. I just walk straight through. Now, ATPCO, Amadeus, and Sabre are the largest distributors of common airline fares. Two of them run a Red Hat's OpenShift, and ATPCO is my customer. What we've done is they hired us and we did a modernization roadmap. 430 airlines, processing data, envisioning. This is available on Red Hat's site if you'd like to download it. And they're using OpenShift. The important part is, here, deconstructed the monolithic into microservices. Automate decisions, remove tribal knowledge, leverage open source to speed to adoption, leveraging containers. It sounds like all of our talks today, right? This is a case example of success. And what we've done is we've saved a ton of money, but they're just moving in to artificial intelligence. And they could not get there had they not done this before. Logisticare. This is a company that does movement of ambulatory services for healthcare. If you're kidney dialysis or whatever, I've got like 3 minutes left, so I'm gonna try and speed through these. What we have is we want to connect and to go through. What were they doing? They were using Borland Delphi. Oh my goodness, how old could that be? That's worse than COBOL. To move discrete microservices. We use Agile sprints, rules as a microservices, and then the most important thing that we did is we had an API strategy. We disintermediated everybody that they would send to the taxi market. They were sending 80,000 rides a month to the taxis where they required older people, not only to get the receipt, to submit the receipt to do it. They wouldn't settle their books for 3 months. We designed an API, my firm did, with Lyft, with Logisticare. So if you have Lyft and you see schedule a ride, we wrote that. And what it does is it allows us to schedule the ride, get our money, get systems, settle our debt, and always have the other ones perfect. And these are the challenges. And success begets success. What Lyft did was, Lyft said, hey, look, if I did it with this guy and I'm generating $10, $15 million of additional business, I'm gonna go to Blue Cross and Blue Shield and say, hey, I've got something that's there. So, and I got the perfect slide. She said, wrap up, and I'm wrapping up. So again, my name is Joe Dickman. I lead Visuri. We're a Red Hat Apex partner. We're strategists. We specialize in this, and our job is to help you understand these technologies. I hope this talk was well. And there's Ellen Wiley over there. She's in the audience. Ellen is my Director of Business Development. My challenge to you is, and my call to action is, I have this technology working. If your organization would like to see how these technologies work in that use case example, please see us, and we'd be happy to get on the line with you on a WebEx and share and show you the components of Red Hat and how we're making these things real. But thank you very much today.
Okay, we have time for a couple more questions. So one from the online Q&A. Do you guys offer consulting to startups?
Yes, we do with offering consulting to startups. It's a strategy, but the offer of consulting to startups is based on business need. What we have to do is understand what we're trying to solve, but we can help you develop strategies. So the answer is yes. Any other questions, guys? If you don't feel comfortable asking them here, please see us. There's a question here. Your question is? Run, Erica.
Yeah, you mentioned about designing the APIs for the couple of cases that you have done. So these APIs you has designed in what languages or what wanted some more detail on that.
The question is, what are the API,
API was designed using Java or maybe microservices or?
The APIs that we use, we've used Red Hat's 3-scale, we've used Apogee, we've used a number of them. What we do is we come in. It is a strategy of using an API. I don't dictate what product people use. I dictate the form and function of separation of interface and location transparency. That'll allow us to block, scale, and to have different content distribution channels. It's an essential component of putting a wolf at the door. It's another layer of security. I think we got a question behind.
Yes, sir. You had mentioned a couple different products that seem similar, and I just wanted to know what the differentiation was. The Decision Manager and the Process Automation Manager.
Very good question. What's the difference between decision management and process management? Process management is disconnected services. It's a subtle endpoint that rests, right? If the decision is that I move from one process to the next, you need an action. The rules are your thoughts and decisions that you will do. They're your principles and your guidelines. If you take it as a human thing, what do you believe in? What do you enforce? And what do you tell your children? And what is acceptable? The way that you conduct your business and the way that you conduct the translations with them is the process. I get information, I evaluate it, I send it to a third party, I receive input, and I move. Those can take days or even sometimes months, right? Long-running transactions that are disconnected. Decisions are immediate and immutable. They're applied to a request for a reply. Here's my criteria. This is my outcome of that decision. If you'd like to talk more, I'll be outside in a short while. It'll be easier. Is there any question here?
I noticed when you built put BPM behind the APIs as a server-based.
Yes.
Have you considered using BPM as a client side to automate the work of the users?
The answer is it is done. The question was, in my diagram, I had BPM behind the scene. What I would really like to do, and we're doing this now for an insurance company, is we're feeding the data that it just comes in from any outside source, whether it's an agent or that, and then it will feed it into the application. I almost want to stop the rekeying of information and allow us to conduct business through other trading partners. So the application may be the feed. I think we're done. We got another one? One more? And then we could catch him outside because I'm over and I don't want to get done.
Is Lance here? You can start to set up.
Come on, Lance,
Oh,
I'm
there.
sorry.
Sorry.
Holding up the line here. Come on up.
So the diagrams you had up on the screens, complex. I'm guessing there'd be like cascading events across all the microservices. So my main question is, how do you manage the complexity of integration and end-to-end testing across
The
different
end-to-end
environments?
testing is first, the question was, if we have all these complex events and such, how do I manage and mitigate the end-to-end testing of these applications in a line? And the answer is, what we try to do is, we try to do enough unit and black box testing around them. And then what we do is we do have people that replace scenarios. So you have to take your models and go through what will happen and then measure those outcomes. And you can do that by actually writing to other streams to validate your data. So as you're going to different endpoints along the process queue, that's where you get your KPIs to say, did I get the correct outcome? And you could use that with test sets of data to say, did this break something? And if you realize when we went back to microservices, if I have my microservices clearly defined, I will only need to test one certain element unless it has dependencies on the other. But that's why we try to write them independently so that they're atomic. I need to step off the stage to let him go, but I'll come down by you. Your follow-up is? I'm listening. Yeah, we'll take it outside. But everybody, thank you very much. I'll be around. If anybody would like to see it, we'd be more than happy to talk to you.
Hi, everybody. I need to get my my laptop displaying here. Let's see if I can do this. Not seeing anything. I can see it there. Okay, all right. Okay. Hey, everybody. Just a little hot. Good morning, good afternoon. It's great to be here. I always love coming to New York. I was actually just here last week for vacation, was home for 2 days, turned around and came right back. But I won't tell you all about that because we're running a little bit behind. I got to get moving. You've heard a lot about sort of back-end stuff over the course of the morning. Today, right now, what I'd like to talk to you about is a little bit about deploying front-end applications onto OpenShift 4, what that looks like, some tools and techniques that you can use to be successful at that. A little about me before I get started. My name is Lance Ball. I'm a principal software engineer at Red Hat. I work on a team called OpenShift Cloud Functions. You can catch me on Twitter at Lance Ball. So if after this we don't have time for interactive questions or you think of something later, feel free to hit me up on Twitter. I'm also a budding ukulele performer. I meant to bring my ukulele so that I could entertain you while builds were happening, but they wouldn't let me bring it on the plane. That's not really true. I just didn't bring it. Okay, before we get started, a quick poll. I would like maybe they've already done this in previous talks, but I wasn't here for them. How many people are deploying apps on OpenShift today? Anybody? Yeah, a handful of you. That's great. Anybody doing Node.js applications? Cool. Okay, some Node developers. How about single-page applications like React or Angular? Yeah, some of you. That's awesome. Any full-stack developers? Yeah. And DevOps? Yes. Okay, good. So hopefully, I'm going to give you all a little something to take away from this talk today. I'm going to cover kind of a range of things. First thing, did you know that, now my numbers are a little bit old, I should start with that caveat, but the #1 deployment runtime on OpenShift Online is Node.js. When I found that out about a year ago, I was shocked, honestly, because as a developer, I tend to think of Red Hat as a sort of very Java-centric, Java-focused company. But in fact, there's a lot of Node.js running on OpenShift. So I started to dig into it, and what I found was that they're not all actually Node.js applications. Many of them, in fact, maybe even the majority of them, are single-page applications like React, Angular, that sort of thing. And the Node component is being used solely for the build process, because with those kind of React applications, you're writing sort of this React stuff that then gets transpiled down to static HTML, CSS, and JavaScript that can then be served by just a basic web server like Apache or Nginx. So I started to ask myself, well, how are people deploying these applications onto OpenShift? Because we provide a lot of different tools and techniques to get your applications up to OpenShift, but nothing really dedicated for these kinds of single-page web apps. So what were people doing? And I started to see that they were doing a lot of they were sort of tweaking some of the Node-focused tools that we had already in place. But myself and folks on my team, Luke Holmquist back there, shout out, started working on some techniques and some tools that you could use to optimize the workflows for things like single-page applications. So with that said, why don't we do it? Why don't we build a web app? It's pretty easy to do because we've got this thing called Create React App. Yeah, here we go. So I'm using a command called npx. Npx, if you're not familiar with it, is a command line tool that comes with more recent versions of NPM. I think it starts with Node 8. But what it does is it looks to see, do I have this executable on my system? If I do, it executes it. If it doesn't, then it'll run off to npmjs.com, download it, and then execute it for me. So this thing, Create React App, is a little executable provided by Facebook to generate a very simple web application. So I'm just going to run npx create react app, my web app. And what that'll do is, can everyone see that okay? Yeah, this font's big enough. It will create a skeleton application, download a bunch of dependencies. It'll actually do a commit for me, and I sign all my commits, so I've got to put in the password there. And voila, I have a Node application. I'm sorry, not a Node application, a web app. So I can just change into that directory, and I can run npm start. And npm start for these things will pull up a development server that watches the file system for changes. And it also loads up in my browser, and it says, all right, hey, look, I got a web app. And it tells me I can edit source/app.js and save that to reload. So I'm going to actually try that. So I'm going to my web app, and I'm going to edit source/app.js and see what happens here. So do H1 and hello, New York. And if I save this, we should see it change. It's updated immediately in the web browser. So that's really cool. That is the kind of developer workflow that makes developers happy and productive. But that doesn't really, this isn't running on OpenShift, right? I haven't showed you anything other than some Facebook technology, right? So we want to get this thing running on OpenShift and be able to do something like that on OpenShift. So how are we going to do that? Move around here a little bit. Okay, so we want to deploy this application to OpenShift. We could potentially use the developer catalog. If you're familiar with the OpenShift console, it comes with like a catalog of different things that you can spin up, and there's an Nginx one right there, so I could maybe just, or an Apache one, I could maybe just tell Nginx or Apache, here's my source code, and like it'll give me a little form. In fact, I've got a browser open to my web console right now. I'm running a version of OpenShift on my laptop. And so if I want to do this and deploy with Nginx, I can click that and do create application, and I see this form here. It's saying, all right, give it a name. We'll say my web app. And then it's asking me for a Git repository. Well, that's not great, because with a Git repository, that means that I'm going to have to actually commit every single little change and push it up to GitHub. Actually, on top of that, because Nginx expects static files, it's not going to do this React build for me. I'm going to have to commit the change, then run a build, commit that, and push all of that, including the compiled artifacts, up to GitHub in order to use this template that's in the developer catalog. I don't think that's going to work for me. That doesn't really seem like the kind of workflow that a developer is going to be happy with. So a brief aside, my wife is a middle school teacher. She teaches at a small girls' middle school. There's about 70 students, and every Monday morning they have assembly, and they talk about the things that went well the week before and the things that didn't go well the week before, and they call the good things roses and the bad things thorns. So I thought I would use the plant-based performance metrics for evaluating what we're doing here today. So we've got a couple of things going on. We've got two thorns. The fact that OpenShift has to pull from our GitHub repository is really kind of a thorn in my side as a developer. Not good. I don't want to do that. And then also the fact that I would have to maintain my compiled artifacts in my GitHub repository. I mean, some people might like that. I personally don't. I don't want to do that. So I'm going to call that a thorn too. But if I can use this Nginx server, then I'm not using that development server that we saw at the first when I was just demonstrating the React application. We're using an actual real HTTP server, which is optimized for serving static content, which is what we're serving with these node applications. I'm sorry, with these single-page applications. So with this approach, two thorns in a rose, maybe not ideal. I really, personally, by the end of this talk, want to get to 3 roses, and I know we can do it. When I started looking at this problem, Luke, actually, back there, my colleague, developed a tool called NodeShift. It's an NPM module. You can download it from npmjs.com. It uses S2I technology. Anyone here familiar with S2I? I'm sure a number of you are. Yeah, S2I is a way to take your source files, and you've got what's called a builder image. And the builder image is optimized for sort of whatever runtime your application is going to be running on. In our case, well, we're building using nodes, so we're going to use a node builder image, I guess. And it takes the local source code, applies that to a copy of the builder image, creating yet another image. And that third image is the thing that gets deployed as part of your application. So NodeShift is using S2I under the hood. It's doing a bunch of things, really. It makes it really easy to deploy an application onto OpenShift with a single command line. You can create build configurations, routes, deployment configurations, all that, image streams, with a single command line. It's great for local development environments because it doesn't depend on GitHub. You can push code directly from your laptop into an OpenShift instance, and you don't have to make any commits. If I want to make a small like spelling change. There's a typo, and I just want to see that change before I commit it, and I actually would like that to be part of a bigger commit. I can do that because I'm just pushing stuff directly from my file system. No commits involved. And like I said, it layers application images using S2I. So I want to demonstrate this really quick. I'm going to use another generator, and this is a Node.js example. So not a single-page application, but I think that we can do this, npx, what is it, express generator? Yeah. So I'm going to create a Node.js example. Again, this does something very simple. It just creates a skeleton, and I can go into my Node.js example directory, and I can type npx node shift -- expose. The expose flag says create a route, so it exposes my application to the world. And then I want to deploy it. I want my OpenShift to know that my application is listening on port 3000. So I do that. And the first thing that NodeShift does is it takes a look at my file system, the local directory, figures out, well, what kind of application is this? It's a Node application. It uses some metadata in package.json to determine what files are part of the application. It packages all of that up as a tar file. So you can see here at the bottom right now, it's uploading that tar file to my local OpenShift instance. And then it's going to run this whole S2I process. It's starting that right now. This will take a little bit of time. So I'm going to jump back to the slides and move ahead. And then we'll revisit this in a minute. Okay, so that's great. I'm deploying a Node.js application, but this is not a single-page application. I could probably make some kind of awkward tweaks to what I'm doing in order to get it to work as a single-page application. But again, it's not ideal. There's sort of undocumented, awkward tweaks for that. It's not a real single-page application deployment. One of the cool things about about NodeShift is that it's really flexible. So you can do things like add or tell it to use a different S2I builder image, right? So we're not going to depend on the Node builder image that it knows out of the box. We want to use a builder image that's optimized for deploying single-page applications. And so as part of the work that Luke and I did, we created a builder image that does just that. It's called nodeshift/CentOS7-S2I-web-app. So I'm going to run this long command line here. Let's see, get out of that. So I'm going to run npx nodeshift Docker image, and I can give it the Docker image, so nodeshift. The image tag flag, is this big enough for everybody? Let me make it a little bit bigger. The image tag flag says we want to use node 10. We have builder images for 8, 10, and 12. So if you have a specific dependency, you can do that. Again, the expose flags tells NodeShift to expose a route. The deploy port is 3000 because that little development server, the React server thing, listens on port 3000. And then I tell it when you start up, the npm run environment variable is npm start. So that tells NodeShift when you're starting the application, run this command npm start. So this thing is going to be working for a little while as well. See how we're doing. Okay, so our node example is done. So let's go over here and see what happened. I can probably find a deployment configuration for my Node.js example. There it is. That's very exciting. And I can actually see this thing running if I go down here to the routes. This route got created for my Node app. And when I click that, of course, we're going to see that in a demo. Application is not available. It might be taking a minute to spin up the application itself. I can reload this in a moment. And we should see our Node.js application up and running. I'll go back to prove that it actually works here in a moment. Okay, and so I think that probably the other node shift process is taking some time to run. So we're going to move on. We'll revisit that in a moment. Now, the problem that I have is that I'm deploying my React application up to OpenShift, but I still want to have the functionality that I had on my laptop, where I make changes locally on my laptop and see those reflected immediately in the browser. And that is possible. It's possible through a command with the OC tool. Anyone here familiar with OC? It's a command line tool. A number of you are. It's very similar to the kubectl command or kubectl command. In fact, it's exactly the same. It just adds more. And one of the things that it's adding is this rsync command. So I can run OC rsync, and I can tell my application, all right, I want you to watch the source directory on my local file system, and then I give it a pod name, the pod of my locally running application, and I'm saying, all right, well, when I make changes to the source directory on my application, I want you to synchronize those with the source directory on the pod. The no perms flag is just saying if there's a permission error, don't barf. All right, let's see. So that is taking a while. Again, all of these builds take a little bit of time, and it's all running right here on my little laptop. So you may have to bear with me for a little bit as things start to spin up. So I will show you this in action in a moment after the build is completed and everything has been deployed. But with this knowledge in mind, we can revisit our plant-based evaluation metrics, and I think now we have two roses. We've got single command line deployment. I deployed my my React application up to OpenShift using a single command line. It created all of the Kubernetes objects that are needed in order to deploy my application and serve it publicly. And the second rose is the fact that I don't have to do any commits. I don't have to push anything to GitHub. It doesn't even have to be a Git repo on my file system. It could just be a directory, right? So I can see changes pushed up to the server easily and quickly. I would call that a second rose. Now, the thorn here is that this thing is still using a React development server, which is not really going to be ideal in production. So we need to figure out what the solution is for production deployments. But again, I'm going to spend a moment to look and see if that's working. It's not yet, so we'll keep going and revisit. Production deployments, OpenShift 4. So let me back up a moment. I gave a talk similar to this in January in Atlanta, and at that time we were running OpenShift 3. 4 had not been released yet, and this sort of production deployment process, I used a technique called chained builds. If you're familiar with chain builds, they're great, they work. I mean, I had no problem doing it, but it was clunky, awkward, not very intuitive. With OpenShift 4, we get something called pipelines. It's based on a project called Tecton Pipelines that grew out of another project called Knative. And pipelines are a really nice way to sort of declaratively specify what kinds of things need to happen in a build pipeline and what resources are required for those pipeline runs to occur. So let's see what that looks like. A pipeline itself is just a bit of YAML that specifies a workflow. Here we have a pipeline that we're going to give it a name, Web App Deployment Pipeline. It expects a couple of resources, a build image and a runtime image. And you note we haven't said anything about what those images are. We're just giving them a name and saying that they're an image. So these are the resources that my pipeline requires. And then it's going to run a task. I've defined the task in another little bit of YAML, and that task is called Web App Build Runtime. So we reference it in our pipeline. and then we specify what the resources are for those tasks. And previously on this slide, we have the build image resource and the runtime image resource. Well, the input to web app build runtime is going to be the build image, and the output from the for the pipeline will be the runtime image. Pretty straightforward there, right? So those images are what's known as a pipeline resource. That also is just a very simple bit of YAML, and it looks something like this. So here we have a pipeline resource. We're going to give it a name, web app build image. This is what the build image looks like. And all it is a URL that points to the internal OpenShift registry at a particular image. In my case, we've built this image using that NodeShift tool. When I used NodeShift to build my application, let's go back here and look at builds, image streams. So we now have an image stream because my build has actually, I don't know if it's done yet, but we've at least created the image stream called my web app. That image stream was created when I ran that NodeShift command line for my React web app. And it's stored in the internal registry within OpenShift. And so in my pipeline resource, I just want to reference that with the URL. The same thing for the production image. At the end of my pipeline, I want to have a production image spit out. I want it shoved into the internal repository or registry on OpenShift, and I'm going to call this one web app runtime. So in addition to pipelines and pipeline resources, we have tasks. Tasks are the things that are actually doing the work. And you can actually run a task independently of a pipeline if you'd like to. In this case, I'm going to show you the task that I've specified for the pipeline itself. But if I wanted to, I could run this outside of the context of a pipeline. My task is named web app build runtime. Again, we have inputs as part of our specification. One of them is an image. And then we have some parameters there like, okay, well, on the image, where are the source files, right? And then we have some outputs, also an image, right? That's what we want to end up with, our web app runtime. And then we have some steps. There's a number of steps in this, and I don't show them all here. But the first step is to take that build image that we created using NodeShift. It's got those static files sitting there, and copy those static files into a mounted volume that then our runtime image, which will be an Nginx image, can copy to its local directory that it uses to serve files, right, in an optimized HTTP server kind of way. So like I said, tasks could be run independently using something called a task run. Here is a task run that's a little bit different. This one is unrelated to what I've been showing you, but this is an S2I task. So as part of the OpenShift pipelines repository, there are a number of pre-built tasks that you can download and use and mess around with, and there's one for S2I. So I can run a S2I task by specifying a task run and giving it some parameters like, okay, the builder image I want to use is this CentOS 7 S2I web app builder image. The path context is source, that's where the source is. And then the input to this is going to be a get URL, like most S2I builds use, right? And the output is going to be this web app image that is a production web app image, but not really production, because if you remember that the S2I process is really just using that React server. What we're trying to get to here for our 3 roses is an Nginx server serving the runtime production image. So in order to do that, we're going to use a pipeline run. A pipeline run is really simple. It just references the pipeline that we've already defined, and then provides the various values that that pipeline expects, like the input image name or input image URL and the output image URL. So that looks like this. we've got a pipeline run. We give it a name, web app prod pipeline run. And then the specification says, all right, we're going to actually run this pipeline called web app deployment pipeline. We want to trigger it manually. There are other ways to trigger it. Today I'm going to show you simple manual triggering. Because of some of the things that this is doing, like reading and writing to the internal registry, we're going to use a service account that has some privileges set up for it. And I should just say that all of this stuff I'm showing you is in a GitHub repo that I have the link for at the end of these slides. So if you want to mess around with this stuff and play with it yourself, you can. And then the next bit of the pipeline run YAML is just specifying what the resources are. And we already looked at those pipeline resources, right? We've got the build image, which was the thing produced by NodeShift, and the runtime image, which is what we want to end up with ultimately. And with that, I think we're at 3 roses. So for development, we've got a single command deployment that allows us to push local code up to OpenShift Online, deploying from the local file system, and we have a method for iterative development, which I am going to show you in a minute. And then we also have production runtimes served by a real HTTP server. All right, so let's look and see if all of our builds and stuff have completed. Let's go to the routes here. No, we don't have a route for our web app yet. My computer is dying under the load of running an entire OpenShift instance. This is where I really wish I had brought my ukulele, so I could like entertain you all while we're waiting for gateway timeouts. Okay, well, we're gonna not do that for now then, I suppose. And move back on. I'm pushing that, that instance pretty hard, I suppose. Okay, so we have 3 roses. One last thing that I want to mention, and then after I get through this last thing, we'll try again with the demo and see how that works. Knative service. As part of OpenShift 4, there's something called Knative. It comes with a couple of different components, serving and eventing. Eventing is not really relevant for what we're talking about here, but we ended up with a production runtime image, and we really need a way to serve that. And an ideal way to do that is through Knative serving. One of the cool things about Knative serving is that it automatically scales your application up if you have more load and scales it down if you have less load, and it can scale it all the way down to 0. Right? So if your application is very intermittent, it's got very intermittent traffic, and you're paying for CPU cycles or uptime or anything like that, scaling down to 0 is going to save you a lot of money. So Knative service is a great way to deploy your applications, and it's very simple to do. Again, it's some YAML, like everything in Kubernetes. We specify the kind as service, but the API version is specifically referencing serving.knative.dev. We have some metadata. We give it a name, production web app. Tell it what namespace we want it to run in. And then we provide some labels and stuff. And then the spec is very simple. It's just telling Knative serving, well, I want you to run this image, and it's going to be listening on container port 8080. That's really all there is to deploying an application through Knative serving. Before we end, I'm going to try one more time to see if I can get my demo to spin up here. It was all working just fine in the hotel about 2 hours ago. But isn't that the way it always is? Yeah, it's feeling a little sad. All right. Well, you're going to have to take my word for it. It's really impressive. what I really wanted to show you was that live coding where I make changes locally on my system, and we see that reflected in the runtime, in stuff that's running on OpenShift. I'm going to just go back to that slide real quick because it is really neat, and I think you should write this down if you're doing any of this kind of deployment. Here, this thing. This is really a very, very useful tool. You can make changes on your local file system, have them automatically synchronized up to a running pod within OpenShift, and if your pod has smarts, like for example, it's using this React development server, then it will automatically recompile and reload that, that source file. Okay, and because I'm like a dog with a bone and I can't give it up, I'm going to try one more time to see if we can get this thing to work. But no, now it looks like my whole local, my entire OpenShift system just crashed. All right. Well, that about does it. Thank you. Here are some links. So the top link is link to the documentation for OpenShift 4. Tecton.dev is information all about pipelines. Knative.dev will help you understand Knative serving that I just talked about. And then finally, all of this stuff, the little bits of code that I showed you are in this repository under my organization on GitHub.
Okay, it looks like we have a bunch of questions.
Oh, okay.
There is one question from online. Do you know when Windows will be supported in containers?
I'm sorry, no, I don't have that
I
information.
don't either. I totally, I used to know, I forgot. Okay, who has questions in the room? I saw a few hands bolt up. Don't be shy now, just because the microphone works.
I know, I explained it all so well. You've got it just burned into your brains, right?
Oh, yeah.
So what kind of resources do I need to run this? Do I need a really hot computer with a lot of memory?
Yeah, well, this laptop has a decent amount of memory, and I typically don't have a lot of problems, but when I put my computer to sleep and walk from the hotel to here, and then put my computer to sleep and walk back to the hotel, and then put it to sleep and walk back over here, sometimes the code-ready containers is what I'm running, which is sort of a local OpenShift instance. Sometimes that doesn't like that. I'm changing networks, and so I think that's what we're resulting with. Sorry?
I'm not running it on my PC, right? I'd be running this on a big production server for a group of people, right?
Right, yeah.
Okay.
Yeah.
Yeah, so I think his question is there anything he should be aware of in production in terms of running code ready?
Well, you wouldn't run code-ready containers in production. You would run just a straight-up, deployment of OpenShift, right?
You mean workspaces or containers?
I think he was asking about workspaces.
Right. So you're talking about containers, she's talking about workspaces.
Okay. So we got a little bit of terminology mismatch here. I'm talking about something that I can run on my laptop. I've got 64 gigs of RAM on here. It usually runs just fine. But when I close and open my lid and put this thing to sleep a lot, it doesn't like that. In production, I'm not aware of what the requirements are for a production runtime.
Hopefully nobody closes the lid in production.
Right. Yeah.
But you're exactly right. I have the same issue with closing the lid.
Yeah. Eventually, if I do it 2 or 3 times, which I should have known better, but.
Okay, any other questions? Okay, well then, thank you very much.
Thank you.
And then Burr will be coming back up to the stage to dazzle us and close out the day.
Let me see how many demos I can bring. guys ready for more? More pain and suffering? All those people online, they've been sitting there at their terminal, writing a little code, answering some emails. And now and then they look up and see what's happening on the screen here. Let's see. Come on, projector. All right. Well, let's actually show you a demonstration. Let's start with a little demo. We'll see if this works, because this is a crazy kind of demo, and it's actually broken on me multiple times. What I want to show you is this concept right here. I have a series of clusters, and the screen is very haphazard, so I have a series of clusters. I have 3 clusters running right now. I have an OpenShift cluster I call Burr. Let's call that my on-premises cluster. And actually, technically, it's running in the cloud, but it could run on-premises. I've done it in both cases. I have one running on Google and one running on Azure. So I have 3 different OpenShift clusters running. Think of them as 3 separate Kubernetes clusters. And the reason I do this is to kind of make the point that if you build your application this way, then your application is fully portable across any cloud provider, any hardware infrastructure, anywhere that you can get CPUs and storage and memory someplace, okay? It doesn't really matter where that is. And then this is what the application looks like. And so if I type in a message here, like I'll just put in my name, hit send request, you notice it says it's responding from Burr. So if I put in my last name here, it's coming from Burr, right? So whatever. It actually adds hola. Any Brazilians in the room? Portuguese speakers? That's how you say, that's the proper spelling of hola, if you're Brazilian Portuguese. So we have Brazilians on my team, so that's why I use that type of hola. But, you put in whatever you want, and you get a message back. Okay, so it's coming back from Burr. And that is because this user interface is sitting on top of that cluster, okay? So what we have is an application workload that's interacting with a local service provider. In other words, this is what we've been talking about today. I have a message producer and a message consumer, and that service is running in that Burr cluster. So here's what it looks like if we go look at it. Let's go over here. Let me see. The Burr cluster is this one. So I'm going to come here. Let's go to workloads and pods. Actually, let's go to deployment configs, I think. This one. So that's the front end right here. So this is the user interface that you're looking at, messaging front end. The worker that's responding with the hola is this guy right here. So let's turn this one off. I'm going to come in here, and I can just say I don't want any of those, so scale that down to 0. Let's go watch our user interface. And we should see that it changes a little bit. Okay. And then if we go pump in a message, let's put stuff in again. Notice that it actually responds with Google, okay? Whatever again. So now Google is the responder to my request. So here's the point of this. The application is the same everywhere, same code base deployed everywhere. But what we've added is another little layer based on the Apache Cupid dispatch router. So this is also known as AMQ router. And that's a technology that we have. It's AMQ interconnect or interconnect router. It's the Apache Cupid dispatch router. It's the name of the open source project. And what this technology does is incredibly clever. It allows you to basically create an AMQP connection, which is a standardized wire protocol across message brokers between clients and servers, consumers and producers, and then distribute them anywhere you'd like around the globe. As long as you can talk TCP, you can basically make this router work. It's not a broker. It's an AMQ router. So it's like a load balancer / router that you would get for HTTP, right? And most people are familiar with HTTP routers, HTTP brokers, or HTTP load balancers, but this does it for AMQP. And so this means that my application can now move about. So in this case, I have it now answering from Google. If I go over to my Google user interface, which is right here. So this is GCP, Google running. Here's OpenShift running on top of it. If I come over here, and let's go here. Come on, Google, load up. And you can see this is the one that's running over here. This is another version of OpenShift. Let me take it down to 0. So I'm taking this message worker, this message consumer, and basically the subscriber, the consumer, the responder, take it offline, and try this again. And let's see, now you can see it's responding from Azure. So basically, we've failed over from Amazon, which was Burr, to Google, to Azure, and if I bring those back online, it'll load balance across the three of them again. You can kind of see that a little bit more. If we go here, makes this a little bit more visible. Okay, so you can kind of see, let's go to show rates, and let's only look at request. And one more time, there's a request processed on Azure. You can see it's processed on Azure. And if I come over here now and add a load balancer to this, let's actually generate some load from Google. And actually, I'll go ahead and bring the Google one back online also. And you'll see that as the workload generator comes online, because the workload is happening on Google, when the Google processor happens, so you can see right there, it's about 2,000 transactions per second, 2,300 transactions per second, 24. So it's basically processing them on Google because the Google message producer is on the same cluster. So this is a complicated demo. We've been using it for a little while, but I really like it. And watch what happens here. Let me go and bring the Burr one back online. So there's Burr. Let's bring it back up. And this is OpenShift 4. That's why the user interface looks different. So when that one comes online, and then what we'll do is we'll go back to our Google one, and let's take it back offline. So we're just constantly just changing, starting these guys up and down. So now we're going from Azure to Burr and Burr to Azure. Okay. And if I want to bring the Azure one online, let's add some load there. I can do that here. So you can just have a lot of fun with it. It's a kind of a fun way to play around with this technology to see that how the load balancing works. And so basically failing over from cloud to cloud, and all the transactions, of course, still work. But again, the whole point of this little demonstration is that once you build your application for this type of architecture, it works across any cloud. Okay? Let's see what it comes back with now. So there's my Azure transactions running right there. There's my Burr transactions running right there. I don't have any transactions running on Google right now because I turned it off, and I can just keep flipping those back and forth. Okay? I want to show you a couple other things, though, as we get into this part of the presentation and kind of illustrate some stuff that is related to actually showing this technology in action. Like this is my cluster that I'm running. That's the Burr cluster right there. You can see it's using about 14% of CPU request, 22% of CPU limit, 25% of memory utilization. Here's my Istio user interface for determining how my Istio applications are performing. I can look at that. I can look at my traceability. I can look at my Kiali console. And so we'll look at more of these in some detail. I can also just pull out individualized metrics as well. And we'll talk more about what those things mean. So we'll come back and look at those screens in a second. Okay, so let's kind of jump into this and rock and roll through some slideware and get back into demo mode, if that's fair. Okay, so I titled this session Serverless or Serverful because one of the things you're going to hear a lot about and you heard about today is this concept, the movement of serverless. We want to have serverless-based architecture. What does that mean? We'll talk a little bit about that here. And then the other concept, though, the opposite of that is it serverful? Serverless, serverful. You get it? It's supposed to be kind of a play on words. But, we're going to have some fun with that. And I want to show you the different, what's happening in the Kubernetes space. And we'll show you a lot more demos just to kind of make it more interesting, okay? The key question, though, I want you guys to have in the top of your mind, in the back of your head, if you will, is your organization. You have to ask this of find 4 vice presidents in your company and ask them this question. You'll get 4 different answers, of course. But are custom apps and APIs a key strategic advantage to this organization? Is it truly critical that we build better software faster and deliver it better to our customers? Or do you regard IT as a cost center? Something needs to be streamlined. Something needs to be outsourced if possible. And the reason you would want this question asked of your vice president is that this will tell you if it's the kind of company you want to work for or not. If you are basically working for a company that considers it a strategic advantage, then you're going to have a lot more fun learning new technology, trying different things. You're going to be experimental. You're going to fail fast. You're going to learn. You're going to try to build better software faster. If you're a cost center that needs to be streamlined, well, we know what that's about. They're trying to find ways to reduce your paycheck and reduce costs as a whole. And that's a very different place to work. And so one great quote from this guy here named Albert Einstein: we cannot solve the problems with the same thinking we used when we created them. You gotta love that. Because in IT, that's what we're dealing with all the time. When we say legacy, it is simply what the person did before us and made decisions before us, that's all. And we had constraints at that time. The technology only worked a certain way. We didn't have a Linux container in 1995. Therefore, we had to do things with big old hardware back then. And as a matter of fact, the hardware we purchased back in 1995 did not fit in a rack. Racks were invented after that. So we used to have machines that looked like washing machines that we had to set up in our data center. So the world has changed dramatically and continues to change dramatically going forward, and certainly in this cloud world. We saw this earlier. You know what your application looks like. And of course, your application, we start thinking in terms of modules and microservices, and we distribute around a network, all with their own data. We showed you this already. So I want you guys keeping that in mind, because this is where we're going from an architectural standpoint, is how do we distribute these components so we can change them independently of each other, all with their own independent pipelines, their own independent teams. But this means we're dealing with distributed computing. So when we say microservices or we talk about serverless architecture, we mean distributed computing. There's a network in between the components. And if you're a Java programmer, a Node.js programmer, Python programmer, C# programmer, it doesn't matter what it is, you have a network hop from component A to B to C. But this gives you independence of that component. I can change this component as often as I want, 45 times a day if that's what I need to do, because it's independent and it's a network call. Very much like your mobile device can talk to a remote website, your mobile device can get updated 45 times a day, or your customer base with their 4,000 mobile devices or 400,000 mobile devices can be updated all the time, and your server side doesn't have to change because there's a network connection between the two. Same kind of principle applies here. Here's the problem with distributed computing. This is a nice Wikipedia entry on the fallacies of distributed computing. Because when you put a network between two things, the network is not always reliable. As a matter of fact, if you've used your mobile phone in any place, around Manhattan, I'm sure, down in the subway system or somewhere else, or in a big tall building, you probably notice it doesn't always work. You think you're going to basically get that connection to happen, and you think the data's supposed to flow, but it does not. The screen doesn't paint all the way. And what do you do, by the way, as a consumer, as a user, when you don't get the response you expect back from that little web browser on your mobile phone? What do? You hit the refresh button, right? Because as IT people, you're helping them. Think about that for a second. We do that too. So, our consumers, if our site is slow and not performing correctly, they hit the refresh button, and we're trying to recover from the error, yet all these additional requests are coming in, and we can't recover from those either. So this concept, I want you to have that concept in your mind, because this is when we get into distributed computing, that's what we're dealing with. My Java component over here trying to refresh against this other Java component over here when it's not responding fast enough. That happens in this distributed architecture, and therefore we have to have additional software infrastructure to help with that. Latency is never zero. Bandwidth is never infinite. That topology always changes, especially in a microservices architecture. So these things will burn you, so just be aware of them. So how do you deal with a failure of a service? If you have a mesh of transactions, basically a request comes in, it has to flow through this set of modules, microservices to get a response. What if something fails? Does it create a cascading fail? This is what we're going to try to deal with next. How do we isolate that failure to ensure that no other component dies because that one died? And you could also have a failure that's based purely on a temporal issue. I'm doing a deployment right now. That caused a failure. It wasn't available. It was being deployed. Now, when you do deploy, you should always deploy with at least 2. Then your rolling update works fine. And maybe we'll see that when we do the demo, right? So I've often made that mistake in my demo. I only have 1. Therefore, you do see the failure because you took down the 1 to bring up the new one. If you have 2, Kubernetes is very clever. It'll say, oh, we'll leave 1 up, kill the other one while we're bringing up the new one, and then only tear down the other one, the second one, when we have 1 online, the new one online. It's very clever about that. So it could be a temporary glitch, though. So in order to deal with all these microservices concerns, we have these microserviceabilities, these capabilities that you have to be thinking about. Okay, and we can spend a lot of time on each of these, but a lot of these are addressed with this architecture we're about to see. Okay, so how do you find another service? If that service is remote from you across the network, how do you find it? In the case of a web browser on a mobile device to a website, you type in the DNS name. You type in CNN.com. Right? You type in Amazon.com. That's how you find it. That's the discovery mechanism. What the good news is in Kubernetes, that's the same mechanism. It uses DNS. The same exact set of principles that work with a mobile device or a mobile browser or desktop browser applies here too. The difference is you don't have to worry about manipulating the DNS Kubernetes does that for you. Okay, it takes care of that for you automatically. Invocation, what is the invocation model? Once I find it, do I speak HTTP to it? HTTPS? Do I speak gRPC? Do I speak AMQP? FTP? What is the protocol I need to use? By default, people use HTTP, and that again works by default nicely within Kubernetes land. Elasticity, I want to make that call across the network. I don't want it to die. As a matter of fact, if a bunch of calls come in, can I scale easily to handle those calls? And Kubernetes makes that easy, right? Scale up, scale down. Is it resilient? Well, I want to basically make the call but not fail. I want to make the call but not wait too long. That's something that Kubernetes does not have out of the box. Okay? So let's talk more about this in a second. In the case of addressing all these ilities, right, that we mentioned earlier, what people have done, what Netflix taught us to do, is put all of that in our application. That's what we did. So our discovery mechanism was a new jar file that we put in our application. Our load balancer was a new application jar, right? Our resiliency mechanism. This was Eureka, Hystrix, Ribbon, and other components like it. All right? We put all that inside the application itself. And this is the world we've been living in up till now, in most cases. But what we have now is this new thing called a sidecar. And this comes with Istio. So Envoy is the sidecar that comes with Istio. And that basically replaces all those other extra components that are part of your business logic, pulls them out of your business logic, separates them, and adds them to this thing called a sidecar. Because a sidecar is like that little thing you add to your motorcycle. You guys familiar with the phrase sidecar and what it looks like on a motorcycle? It's a little thing where you can sit in. Here's the difference between a motorcycle sidecar and this one. The motorcycle sidecar is an attachment that the person rides along with. This sidecar can take over the handlebars, the brakes, and the accelerator. It takes over the car when needed, okay? And therefore, because of that, it can do all kinds of really powerful things, okay? It intercepts all inbound, outbound traffic. So this is really the concept of service mesh technology. You basically have this now, this intelligent routing, load balancing. You can do these really clever canary releases. I showed you some of that in an earlier presentation. I'll go through it more slowly in this case. You can inject faults as well. In other words, you can self-injure, which is kind of awesome. You can introduce chaos into your application infrastructure. People think that's super cool because if you have a distributed architecture, you want to know that it is resilient to failure. You want to test for failure. You want to cause failure. And we learned about this also from Netflix. Netflix gave us Chaos Monkey. It's called Chaos Monkey, and you'll see it as a little, funny-looking monkey. And what it does is it literally goes out there inside their infrastructure and kills things. So you have that same basic concept here. In the case of Istio, you can inject different HTTP faults, like throw up 500s randomly and see what happens to the software, if it behaves poorly or better. Or you can actually introduce latency. You can basically add a 7-second delay amongst 20% of your transactions and see what happens. A variable could be your whole system comes crashing to down. Observability and telemetry are part of it as well, as we did in addition to security, like encryption and authorization. So additional security capabilities are also part of this. So this is meant to sit over and above Kubernetes, over and above OpenShift, okay? And it looks like this. If you look at my data plane here, I still have my Kubernetes pod with my little container running in it, with my JVM or my Node.js or my C# or whatever it might be. It has my application code in it, but the sidecar sits there beside it, and traffic flows through the sidecar. HTTP1, HTTP2, gRPC, TCP with TLS, that traffic flows through the sidecar, and the sidecar intercepts all inbound and outbound traffic. That's really how it's doing it. Okay, it's hijacking all the traffic, and it's looking at those bytes that go in and out and manipulating it. So you can see the traffic flows through the sidecar from component A to component B to component C. Okay, by default, with regular Kubernetes, the traffic flows through the way the normal traffic flows, right, through your application. And then you can see here's the control plane, and there's these primary components, the galley, the pilot, the mixer, and the citadel, right? So these are the guys who are kind of controlling all those different sidecars that are running out there. And this is why you need this, right? If you have 1,000 microservices, you have 1,000 sidecars. Therefore, when you update your network topology, because that's what you're doing here, you have to update 1,000 sidecars, and you can do that manually. People do this today with Envoy today manually. You can go into each Envoy and say, hey, tweak your settings, tweak your settings, tweak your settings. Or you can go to Istio's pilot and say, tweak the settings one time, and it goes out and makes sure that all the envoys are up to date. So that's really the difference here. You can always manipulate Envoy directly if you want to, using it just as you see here, but you don't have the control plane, and that's really what Istio gives you, right? So Istio Pilot, Istio Mixer, and Citadel. So to kind of look at this thing, let's actually look at how it's implemented here on my platform. I showed you this earlier, kubectl get CRDs, okay? So you can kind of see I have a bunch of CRDs here, and there's ones for Istio, and there's ones for Knative. I also have Knative here, and I think I mentioned I have Kafka here too, right? So Kafka. And so the get CRDs, grep Kafka. Kafka. Helps if you spell Kafka correctly. There we go. So I have a bunch of different things. And these CRDs came to be. You can create CRDs using the standard kubectl command line, or you can basically use the new operator model that's part of OpenShift 4 and install it that way. So I showed you this concept of the operator hub, and you can kind of see like what else would I want to install. So if I want Akka running here, if I want AMQ interconnect, which is the router technology we were talking about, here's Kafka and AMQ streams. I might want Spark running here. Whatever it is you wish to run. Camel, this is actually a very cool one in this case. This allows you to create an integration operator, which means you can deploy integration objects to your cluster now. And so the idea is very simple. You just deploy these different objects. So if I come over here, tutorial. I'm just going to show you some examples of what I mean by these custom objects and how you deploy them. So here's a normal everyday object that you see in Kubernetes. It's called a deployment. So deployment is something you do all day, every day with raw Kubernetes, okay? You basically create this thing called a deployment. You call it a YAML. You give it some basic information like labels. That's all interesting, template, whatever. But the part that's interesting is what are my environment settings? What is my image name? So this is an image coming from a repository of some sort. And this one comes from Quay.io, but it could come from Docker.io. It could come from your internal repository. You say your image pool policy. And never forget your liveness probe and readiness probe. So those are mission critical components to have as the liveness probe and readiness probe. And basically, this is actually how all the magic in Kubernetes works. If you forget these two probes, you lose most of the magic. So make sure you have these two probes set. Because what these two probes do is basically it's a two-stage process. Whenever Kubernetes goes to launch your application, it says, first, are you alive? And if you don't pass the live, I'm alive check, it assumes you're dead, right? Makes sense. If you're not alive, you're dead. But you're there, you're walking around, so really what you are is a zombie. You're a zombie who doesn't respond correctly, so what it does is it shoots you in the head and starts you again. So you need to make sure you pass your liveness check, all right? Now, notice my liveness check, and this is my readiness check. I kind of use the same thing all the time, right? It's an actual HTTP call. It can be a curl call, HTTP call. It can even look at the file system. So if all you have is a batch application, it can look at the file system to see if files go in and files come out. But this is critical to pass this test and identify this test. How often do you want to be checked, and what is the actual business logic endpoint to call? And then the readiness probe is the second phase. The readiness probe says, okay, you're alive. Now let's put you in the load balancer. You ready for load balancing? You ready for user traffic? And the answer to that could be yes or no. Yes is 200. No is something beyond 200, like 500, if it's HTTP. So you decide exactly how you'll set those business logic components up. But with the readiness probe, it's incredibly powerful, okay? You can now decide in your business logic if you're ready to receive user traffic. That means, one, my container has booted, obvious. My JVM is warmed up. Hopefully that makes obvious sense too. JVM may take a little longer to start. And also, I want to connect to my databases and populate my cache. You might want to do all of those things before you are ready. And before that time, you would return 400, 500, something like that. And when you have checked all those things inside your business logic, you return a 200, and then you get user traffic. And so this becomes incredibly important. So I show this concept in my intro to Kubernetes class, but it's an important thing to understand because it's a lot of how the magic happens here. Okay? But let's show you what I mean by custom resource definition. Not those. What am I in here? Sometimes I never know what I'm looking at. Okay, so here's an example of a custom resource. Okay? So we have this concept of a CRD, or custom resource definition, on this cluster, and it supports virtual services. or destination rules, or policies, or Kafkas, right? So you can see we can then define a document on the end user side called virtual service, or I can find a document out here called, what's this one, metric. I can find one called a quota. These are additional components that have been added to my cluster because I installed Istio CRDs on top. If I go over here and look at my, let's see if I can find, let's see here. Dun, dun, dun. Here's what a Kafka broker would look like. If I want a Kafka broker, here's a simple one. Okay, well, maybe that's not so simple. Let's find a more simple one. Oh, here you go, even more simple. Okay, and I even named it for the guy who was in my class last, Arun. So you have a Kafka kind here, and you just deploy this Kafka object. You say you want 3 of these, and you want it to be externally routable. We just say ephemeral storage for now, but I want 3 zookeepers, and of course that will give me 3 replicas of that, right? So I'll get 3 zookeepers, 3 Kafka brokers. So that'll end up with 7 total pods. Let's actually see if this will work. Obviously I didn't test this. Why not? Okay, so kubectl, create namespace. Let's call it Franz. Franz Kafka, you get it? Okay, so I'm typing in this little window, come on. The cluster's a little slow, remote for me, there we go, kubeNS, Franz. So kubeNS is a special tool that allows you to basically make that sticky, so you don't have to type the namespace all the time. So if I type kubeNS without that, you'll see that Franz is highlighted there, so it's the sticky one, I don't have to type it anymore. And so kubectl apply -f kube files, and then what was that called? Hello Kafka? Let's see there. Get pods. All right, there's 3 zookeepers already coming up, but let me do this. kubectl get Kafkas. So you can see, I can say, I now can refer to that object, Kafkas, as if it's a real thing, because it is a real thing. It was not there in regular Kubernetes, but it's there because I've installed the operator and the CRD, and now I have Kafka support for my cluster. I have virtual service support if I want Istio. If I'm using Knative, I can use the Knative service. So everything you install on top of a Kubernetes cluster is now done this way, and that's why I'm trying to make this point. I recognize this is a super advanced idea, but this is where you get to see all these fancy extensions. Okay, but everybody adding operators and custom resource definitions on top. You can then, of course, do things like kubectl describe Kafka, Arun cluster, and let's see what, and there I'm describing it. In other words, the object is just like any other object that was traditionally part of Kubernetes. I can describe it, I can get it, I can CRUD it, right? Create, read, update, delete it. I can do all the things I previously did to it. And you can see my zookeepers are coming online there. We won't wait for them. But as soon as those 3 come online, you'll see the 3 Kafka brokers, and then you'll see the operator installed, and all that will get installed. And of course, all this is taking memory on my machine, my cluster. So we should see some of these numbers move up here too as those guys come online. Okay? But let's show you some more things here. Let's go back here. Okay, I showed you this earlier, but I'll show it to you again. Okay, I have this application, customer preference recommendation. It's basically running as kubectl, kubeNS tutorial. Okay, it's these 3 pods running right here, customer preference and recommendation. If I look at the GUI, it's running over here. So let's go to pods, and let's switch to this one. By the way, the other one was called demo 2. That's this one, the one we showed you, the routing across the multiple clouds. Here's Franz, the Franz we just did. But let's do this one. I call this one tutorial. You can see there's a lot of different namespaces here. So there's customer preference and recommendation running as the 3 pods. Keep in mind the pod is the thing that's making your application run, right? That is the computer, if you will, from the application standpoint. And to kind of make that point a little bit more thoroughly, let's do this. I'm going to come in here and look at the code base for this application. I showed it to you earlier, and I was actually just playing with it. I changed it from my name to my sister's name. So let's actually... is there a David in the audience? Got to be a David around here someplace, right? We'll make you the star of the show. So David Mendation here, instead of recommendation. David. I'm just changing the Java code. And then again, this is Quarkus Java code, so you can see it's at path, it is at get, at put, at get, things like that. It's pretty standard, everyday JAX-RS, JPA kinds of application. I can compile it and then deploy it. So let's do that. So we've saved our code. Let's do a Maven clean package, and I'm going to skip test because I changed it. Okay, let's go ahead and do our Maven. And there we go. And this allows me to, as a developer, to test this locally. Okay. Quarkus also has a really nice feature that basically has a live development mode. So I can actually have it in live development mode, make changes, and just refresh the browser. So edit, save, refresh, edit, save, refresh. In this case, I'm not doing that. I'm doing a real build. Okay. That creates this target directory, and it creates this snapshot runner. So that is my fat jar. So I can say target, boom, run it. Okay, now it's running. Let me stop this. Curl localhost running on 8080. All right, so there is the David Mendation v2. And notice it says unknown here. So unknown is specifically this concept of the, where'd it go? It's the get or set host name from system.getEnv. In other words, I'm asking in Java, what is the computer I'm running on? This becomes important later. Right now, when I'm running in this local host environment, no big deal. But we'll see that in a little bit. But there's my application running. You also notice there's some logging there. It says David, on the logging side, unknown 3. So that's all good. So let me go ahead now and do something a little bit fancier with it. And if you remember, I ran some scripts earlier. Let me show you what those scripts did. Okay, I'm not trying to hide anything here. Let's see, there's that script, and then this one. This is the first one we ran. So there's the Maven clean package skip test that we did there. And then we did a Docker build. Okay, this is a standard Docker build command. I'll just copy and paste it over here. I'm going to do a Docker build now. All right, there it goes, Docker build. So now I have a Docker image built against my local Docker for Mac running right here. Okay, Docker images, and I can grep. Don't go there, Versetter. So there's the, let's see here. I just did the recommendation, v2, down right there. It was updated 4 weeks ago. Nope, that's the wrong one. I got too many of these things here. Not the Quail version 2. That one, 41 minutes ago. That sounds kind of funny too. Oh, there it is. 15 seconds ago. I found the right one. So that is the one we just updated. And if you look here, it gave us this container that was built, this image that was built. Now the next step is actually to push it out, okay? So you have to tag it. So let me do that, Docker tag with that image identification, and then I'm going to tag it, and then we're going to push it. So let's do that, Docker push. So I'm pushing it now to my repository, right? In this case, it's going to Docker IO, but it could go to anywhere, right? Quay IO or anything for that matter. If I go to look at my Docker repository, let's hit refresh. It should say updated a few seconds ago. Okay, good. So that is the one we just updated. Okay, but if we go back and look at our application again, just hit it. And by the way, when I say the application, it's this one right here. Okay, so that same one. Look at it over here. So this same one. Okay, that's the one that we're talking about here. And I just have this curl command hitting up against it. What I don't have is a second deployment, get deployments. Oh, get deployments. All right, I have recommendation v1. So if I look at my script that I showed you earlier, right, it basically did this kubectl apply and the deployment YAML. Notice also, though, it did this istioctl. So this is where it gets a little bit interesting. So this is what sets a regular deployment apart from a istioized deployment. It's this one little trick. If I look at the file, and actually let's do this. Let's just open up this file. Here and here. Open up that file for me. There we go. Here's, if I showed you a deployment earlier, okay, same thing we're kind of expecting here. This one, of course, points to Quay.io. The one over here, deployment, v2, points to Docker.io right there. Okay, so that guy right there maps exactly to this guy over here. That's the one we just pushed up there. So it doesn't really matter. You just have to figure out where the document is. In this case, it's just a YAML file sitting on my file system. But notice there's nothing funny about it other than this istio inject equal true. But what we're going to do is have istio.ctl, inject everything else it needs. And the way it does that, and actually let me double check my command here. See, it's basically cube inject -f and the file name. So if I say kubectl, istio.ctl, cube inject -f, deployment v2, and you'll notice there's a bunch of other stuff now, a whole bunch of other stuff. This is where that sidecar gets added on, okay? You can basically see there's proxy v2, and then you'll notice that the whole sidecar is coming to be, right? So this is actually the sidecar, how it's configured. You can see there's actually, you can actually SSH into it and exec into it and look at it from a port standpoint. There's the Envoy binary. That's how you know it's Envoy. So that's how the sidecar gets added through this one command. So if I do this, let's do this real quick. Right here. And there we go. Well, let's go back to polling. And watching. So right now, because I've hit it with that second deployment for recommendation v2, you can see it's going through its initialization process right there. As soon as it gets through the 1 of 2 and 2 of 2, then it's ready. So in other words, it's got to load up this container with its sidecar container. That's why it's 2 of 2 now. By default, normally you would always see 1/1 because there's always one container. But with the sidecar, it's 2/2. And then since it has to be live and ready, you saw those probes earlier, you see it going through the process here. That's why it says 0 of 2 are ready. When it goes live and ready, you'll see 2/2, and then you'll see it part of the load balancer. And there it is. So 2/2, and now David Mendation is part of the application. So this gives you a little feel for how to do the basics, and then what I showed you later was how we actually do something that's a little bit more fun than that, which was, let's do this. Let's switch this up. And okay, and we'll do this. So yeah, I'm just changing windows here a little bit because I have so little screen real estate to work with. So that's, by the way, if you want to understand how that works, kubectl get services, get services. You can see there's the recommendation service. If I say kubectl describe service recommendation, come on now. Recommendation, you can see there's the selector app recommendation. If I say kubectl get pods, show labels, you'll see that both v1 and v2 have the app recommendation label right there and right there. So that's it. The labeling of the pods allows you to basically get both those inside the load balancer. So this is default Kubernetes behavior, and if you want to, again, modify it using the Istio technology, you would then apply one of these rules. And so let me show you what that looks like. Let's kind of look at one of these rules. Here, I'll show you what the script looks like, and then you can kind of see what it looks like. So here's the, we won't need to do a replace, but let's do this one, okay? You can see it's basically doing a kubectl apply, Istio destination rule, recommendation v1, v2, and then a virtual service rule, 1 and 2, okay? So in other words, those are just YAML files also. You're living in a world of all YAML these days, and you just have to execute those. So I can basically just copy and paste these if I want to. All right, come on now. And then let's do this other one. I'm just copy and pasting from the commands here. Let's see if that worked for me. kubectl get vs. Yep, there's the recommendation vs. Virtual service, get dr. Okay, so now, and it's all v1. So if we go kubectl describe vs recommendation, you can see it's 100% weight goes to version 1. So this just simply means you can manipulate the traffic any way you want, okay? And then, like I said, you can do all these really fancy deployment models. Now, the one thing I didn't show you earlier, I just want to walk you that a little bit slower, was because you've done that, you also get the tracing. So in other words, I can see the transaction path through the system. I can look here at, it goes from customer to preference to recommendation. I can see how long it takes at each one of those sub-transactions, because it could be that the user is complaining that the system is responding too slowly. Well, whose fault is it that's too slow? Well, the customer team is going to say, it ain't our fault, we're responding great. The preference team must be at fault. And the preference team is going to be like, no, it's not our fault, it's the recommendation team that's the slow one. That stupid AI engine takes forever to respond. And I don't know if you've worked with an AI engine, but they can be pretty slow because they need lots of CPUs. I actually worked on one demo application where we had 140 cores in the cluster, 120 had to go to AI. So you have to think in those kinds of terms, right? It takes a lot of CPU or GPU if you have it, but you can kind of see that recommendation does okay, 0.33 milliseconds. Okay, preference is a little bit longer, but you can use this tool to kind of see what's going on there. We have another tool called Kiali, and you can see with Kiali, and you can see something kind of interesting here. You'll notice V1 is green, V2 is gray. That's because all our traffic is flowing to V1 right now. So you can kind of see that in the little animation as well. So Kiali allows you to see this thing graphically, understand the performance and behavior of the application, and more importantly, if you have errors, like one of the things we show you in the Istio talk is that we can make V2 have errors. Because if we're practicing fast cycle deployments, that thing could have an error in it, in which case you'd see that here. So proactively, you can deploy the canary that no one sees, look for errors, look for problems with memory and CPU utilization, look for logging issues, and then you would see those errors through the various observability tools. So this might be the only win you get out of Istio is just these nice observability and monitoring tools, and that's a huge win for you. So you got the Jaeger, you got the Kiali, and you, of course, have your Grafana, and you can kind of see here's the performance characteristics. Let me refresh this, of customer in this case, right? You can see we've had some errors here or there, but otherwise it looks like it's doing pretty well, okay? And you can kind of just explore all that when you have Istio on top of your application workload, on top of your Kubernetes cluster. But let me show you one more thing, all right? And because there's one other element of this I want to make sure we show you, and that is, in this world of microservices, we talk about functions. So Marius mentioned this in his presentation. You've heard it before. And also, Lance just talked to you a little bit about Knative. I want to show you a little bit of Knative as well so you can get a feel for where we're going with this. So the concept of Knative means I want to have a function-based application. And the concept is that I want to think about my application no longer in terms of whole big chunks of business logic, but small chunks of business logic, like my microservices right here, right? And that's kind of what we've been working with, or functions that basically build up the overall application by leveraging existing services, functions that wire things together dynamically, and whole microservices that really make our business logic up. And so you have to think about in terms of how your next generation architecture, where can I use a function, where can I use a microservice? And the cool thing about Knative is it blends the world. There normally is a difference between a function programming model and a microservice programming model. With Knative, it can make your microservice behave like a function because it gives it a dynamic scaling event. So all right, let's show you that real quick. Okay, we only have a few minutes left, so let's kind of see if we can make this thing run. Okay, so here, kube NS, side by side. I just want to show you a simple example that I have. Let's see how it works. I'm looking for my pods. I have no pods running right now, okay? Here's the part that's kind of weird about that. kubectl, get deployments. In this namespace, wow, I can't type. I've got this thing called booted, node, and quarked. So this is Spring Boot, JVM mode, Quarkus compiled to native, and Node.js as Node.js. I have 3 different deployments. I have these things called K services. 3 different K services. Notice the K services have a URL. The K service is another one of those CRDs I spoke of. It's another custom object that's been added to this cluster that gives it this Knative capability. And what it means is it knows how to scale from 0. Okay, so kubectl get pods. So let's try that real quick. Can burst. So let's say a bunch of load comes in. In this case, 40 transactions just hit the server right now. That's what I just did. So it's a simple script using this thing called Siege, all hitting those URLs you saw earlier. And so, kubectl get K service. So you can see what the URL is. You could also hit these URLs yourself. But notice what happens. We have 4 pods now coming to life because we have 40 users asking for something right now. And the way I've configured Knative is to basically kind of go into panic mode and go, holy crap, 40 users, start 4 pods. You can decide what that ratio should be. But notice, as soon as the first pod is up, my user gets an answer. My 40 users get an answer. So if I come over here and hit it again, okay, it comes back fast the second time because there's pods up now. Until the pod is up, there's no computer to respond. You'll notice that this right here also is part of the actual transaction. So let me actually go into my poller. And you kind of see right there, you see that the 549 CDF? 549 CDF, which one is that one? Oh, it's not. Oh, C5, interesting. CP, oh, this one right here. So it's that one right there. I was looking at the numbers incorrectly. So this is the guy that was responding. Oh, now it's this guy is the one who's responding. Okay, now you can see right there. That is the computer it's running on. And here's the thing that just happened that's kind of cool. Because I didn't really need all that extra server capacity now that the panic is gone, the overwhelming load, Knative is saying, you know what, let's start tearing these things down. You don't need all that memory and that CPU being used. As a matter of fact, if I stop the polling altogether and you wait about 90 seconds, and let me go ahead and bring up Node.js, by the way, and I'm also going to go ahead and bring up Spring Boot. Okay, well, actually, let's wait a second for Spring Boot. Let's let Node come up first. So Node is going through the same process. It's got overwhelming load, 40 users coming in right now. So let that go. And while that's occurring, let's actually look at our monitoring one more time. Let's come over here. So one of the things we can monitor is container memory. So this was our Quarkus application right there, running about 20 megs of RAM. So for those of you who know Java, you're like, what, 20 megs of RAM? That's insane. That's not possible. And that's because Quarkus does that compile to native trick. Okay, and you can kind of see that. So there's our Quarkus application. This is the one that's still up. The others, the other 3 died, right? They got terminated. But let's go over here and look at our Node.js. Okay, Node.js is up. And let's kind of pop it one more time to make sure Node is happy. Whoop, come on, system. There we go. And so Node.js is up now. Let's hit refresh over here. And let's see. So in this case, Node comes in around 30 megs, and Quarkus Java came in around 20. Now, these numbers vary. Every time I run this, they're different. But the point is, they're almost the same. Okay? So Java and Node are about the same size, and they operate and start at the same speed. And this is pretty unheard of in the Java community, so that's why we make this point. But there's my Node application. Let's go ahead and bring up the Spring Boot application. We'll do the same thing. And what I'll do, let me continue polling it so we don't let nothing goes to sleep. Because by default, Knative is set to basically start, if you're not touching these pods, it starts tearing them down, right? It starts killing them. And I don't want to kill them just yet. But this is really the point of Knative, is the idea is that you can start with nothing running at all and burst and scale out. So that's really its gift, the trick that it's doing. It can hold the load, absorb the load, and basically through HTTP load, and then dynamically scale out based on that burst of traffic, and then stabilize how many pods you really need based on the traffic that you sustain. And if your traffic goes away, like it often does on Sunday night at 1 a.m. in the morning, then you have no pods running. You're not paying for any memory or CPU, and your cluster now has that available CPU and memory for other jobs. Like now I want to run my machine learning algorithms. Now I want to run my Spark workload. Well, now you have additional capacity in the cluster because it got scaled to 0. So you can kind of see these guys are all going. There's our Spring Boot. Looks like Spring Boot came up. Let's check it out. Yep, there it is. So now that's over 110 megs of RAM, 104 megs of RAM for the Spring Boot application right there. Okay, so that's a normal Java application. That's not has no Spring Boot. Okay, I just want to kind of give you guys a feel for that so you have a feel for what we mean by serverless and what's happening with Knative, give you a feel for how these things work. You can kind of see that we need to basically wrap up and finish up the day, but you can deal with your microservices, which are typically long-lived processes that are under your control. You can decide when they start, when they stop. The function kind of is, the cloud determines when it starts and stops. The nice thing about it, though, the programming model is identical when you use Knative, and of course, it's fully portable across any cloud provider. Okay, I can run this on any cloud that I decide to install this into. There's also this concept of function as a service. This is not a function as a service solution, so keep that in mind. Knative is just applying really clever serverless-like scaling principles to what is happening here. There will be function as a service technology that shows up in the Knative ecosystem over time, but right now there's not one winner. Okay? So Knative does things like allowing you to do this auto-scaling, helps you build images, help you with your dynamic routing. We could spend a lot more time, but we don't have time for that. Let me just double check that we've hit all the high points. Lance mentioned Tekton to you, so definitely check that out, which is a solution for build. And then I have a bunch of items here in this presentation deck. By the way, the presentation deck is at bit.ly serverless or full. That'll get you access to the deck. But then you have access to all the links, all the books that are available for download. And of course, if you want to join me for one of the Safari Live things I do a 3-hour version of this presentation as opposed to the 45 minutes that we have. And we are officially out of time, is that right?
Yes, it is. Okay, so wait, before you start clapping, I'm going to ask for questions because that was a lot, and I hope you guys have some because that was super interesting. Do you mind going back to my slides?
Oh,
you still
yeah.
had them up? And down right there.
That one.
Next one.
This one.
Yeah.
All right.
Okay, so I'm just going to leave that up there before I talk more about that. Who has questions for Burr? No one? You guys want to get out of here? Okay, so
Your brain is melted at this point.
Yeah, right? Yeah, let me get up here. So for those of you in the room, as Joe mentioned, there are surveys on your chairs. Please fill those out and drop them off on your way out. And then also Burr's book is available. So for those of you that did not grab it at lunch, please grab that on your way out as well. And if you are interested in attending any other New York City events, at the same table with the books and where you'll drop off the surveys, they will give you some more information on those. And just a reminder, for those of you in the room, you will receive an email from Kelly with the recording and the slides and all of that stuff tomorrow. And then for those of you on the webcast, those will be available tomorrow in the same links. And let's see, anything else? I'm good? Oh, yes. Yes, thank you, Missouri, for co-sponsoring. And I hope you guys really learned a lot about, oh, yeah, there's a question. Okay. Well, I hope you guys
Now she's going to chase you down with the microphone.
I hope you guys did learn a lot about microservices, event-driven development, OpenShift, Kubernetes, Knative, you name it, we talked about it.
You mentioned something about Kubernetes and DNS, that you use Kubernetes to play with the DNS. What do you do there to help you managing the DNS and hiding DNS servers or something if the container is not
So
up?
when I showed you that concept of how it uses these label selection from the service, get services, this service has a name. See right here? If it helps if you spell the word services correctly. See, the name is called quirked whatever, or it was called customer preference recommendation. In your code, that's all you do. You simply say, I want customer, I want preference, I want recommendation. That is, in fact, the DNS entry for that. You don't have to worry about it, right? It's just, as long as you declare a service, which you almost always do because you want to have something you can talk to, then that's what, it's the DNS name as well.
Okay, thank you, everyone.